Hi guys, BuildZoid here, and have you ever wondered what does it take to degrade a Ryzen 7nm processor? Well, today we're going to be taking a look at one answer to that question, and I say one answer because there's many answers. Yeah, so let's just get into it. So what we're looking at here right now is my 3700X crashed in Cinebench R20 at 4.175 gigahertz. Right? Like, actually, wait, we can zoom in on this a bit. Like, the dodgy way. There, see? So, well, 4166, but that's because the BCLK reading is a mess. So, it's at 4175, and it's crashed in Cinebench R20. We're going to rerun this. The issue is, like, getting it to crash isn't super reliable. I think this is, like, the fourth run, or third or fourth run of Cinebench. Before it crashed, and a lot of the time it just blue screens the whole system. So, yeah, interestingly enough, like I'd get an IRQL not less or equal. So let's open up hardware info because I want to check that the temperatures aren't completely out of whack, because that's just a thing you need to keep track of. Is just like, are the temperatures still good? And they should be. We're not running that much voltage right now. Well, actually no, I want die temperature, or that one. Either of those works. So, let's run our Cinebench. Hopefully it doesn't crash. Yeah, we're just like low 60s right now, so the room's pretty cool. If you run it a couple times, then the AIO heats up, but you know, it'll still be somewhere in the 60-degree range. So, reasonably cool. You know, reasonably cool. Not pulling a whole lot of current because it's a Ryzen running Cinebench. Cinebench isn't that heavy. And we're only at 1.3 volts and 4.175 gigahertz, so it's really not pulling that much power. It's not getting really that hot, but before I started this experiment, this chip would run 4.175 gigahertz indefinitely. Like, I didn't crash. It just didn't. So the whole reason I started with that crash message was like, it crashed. Like, that was the whole point. That's about as much proof as you get for degradation. Like, unfortunately, like, admittedly, when I first started this, my goal was to shave off like 100 megahertz off of this chip. Currently, it looks like I've shaved off maybe 25, maybe 50. I'd say 25 because 4.175 doesn't work anymore, but previously the chip would kind of run 4.2 with this level of voltage, but when I say kind of run, it would like run 1 or 2, maybe 4 loops of Cinebench before crashing. Now it doesn't run any loops of Cinebench before crashing, or at least it shouldn't run any loops. We're gonna check that. Actually, you don't need to see the postcode. So we're just gonna go up to 42. And at this point, it should just insta crash, and it's nice and cool. It's not like it's running super hot or anything. Because that's the thing is, like, after the torture test that I was running, like, you need to let the cooling system cool down. Because AIOs, you know, like, they're great. The thermal capacity is great because they're slow to heat up, but that also means they're slow to cool down. So where is it? Actually, we don't need hardware info. We just need Cinebench. So this should just lock up. And watch as it runs, just because I turned on the camera. It's also super unreliable. Like, sometimes it crashes really early, sometimes it crashes towards the end. There we go. Okay, man, I was getting worried. I was like, wait, is it going to finish? Please don't do this to me, you stupid pile of trash. So anyway, yeah, it crashes. It crashes quite cleanly. So 4.2 doesn't work at all. Previously, it kind of did. 4.175 kind of works. Previously, it worked perfectly. So we're just going to drop it down to 41, and I'm going to show you the settings that it's been running for the last, or it's actually not been running exactly these settings for the entire 67 hours. There was 2 hours that were spent at slightly higher, more aggressive settings that unfortunately they were tripping the over temperature protection, so I couldn't run them for extended periods of time. And when I first started doing the testing, I was running significantly less voltage, but basically it wasn't degrading fast enough. So I just kept raising the settings until I got to a degradation rate that I was like, okay, this is actually doing something. And well, actually, it wasn't even that. Like I just kept raising it until I couldn't raise it any further, and that's what we're at right now. So if I open up Prime 95, and I should not have done it in this order. Should have opened up hardware info first. Oh no, no. So, and what we're gonna run, and this still runs. Like we're running a ton of voltage, so you know, that's the thing is like I can't really. I'm not running the CPU at the edge of its stability for the torture test because we're here to like I want it to run for like hours at a time and just take damage constantly. So it's going to take a little while to ramp up in terms of the temperatures, but that gives me time to talk about the settings. So as you saw in the BIOS, I punched in 1.5 volts. Now, there is medium LLC on this, so we are drooping down into the 1.44 volt range. So we're not actually running at 1.5 volts. So 1.44 volts is extremely high already, and I can't raise the voltage any higher because the over temperature protection on a Ryzen CPU is 115 degrees Celsius. And with how unstable the room temperature is in this room, it would sometimes shut down. Like right now, what is it? It's 3 a.m. or 4 a.m. or something. It's 4 a.m. So right now at 4 a.m. it's pretty cold in the room. At like 12 at noon, with me, you never know if by 12 I mean midnight or 12 I mean midday. But anyway, so at midday, we'd be hitting like 111, 112 degrees. And so if the voltage was any higher, it would hit 115 and it would shut down, which I found out the hard way when I was trying to run 1.52 volts, because again, like I really like my goal was to shave off 100 megahertz in like 24 hours. I did not manage that. I did not manage even anywhere near that. I ended up running these settings that we're running right here, right now, or similar settings to what we're running right now, for 67 hours, and finally got like 25 megahertz worth of degradation, which is like, yeah, so Ryzen is really tough. It is really tough. So you can definitely degrade a Ryzen CPU. It's very hard. It's extremely hard to do this, apparently. Though, or at least it's extremely hard to do this with this CPU specifically. And the reason why I point that out, because this isn't really a great test. Like, the data from this test is just so useless, if you actually think about it. Because like the reason I don't do this kind of testing most of the time is because this data is completely bloody worthless. Why is it worthless? So first of all, I've actually seen like a long-term reliability test from a chip manufacturer, and with say 200 chips, they'd have a failure rate after 1,000 hour of accelerated endurance testing. After 1,000 hours, they'd have like a 3% failure rate, as in six out of the 200 chips would no longer meet specification. That doesn't mean that all the chips weren't degrading. It just means 6 of the 200 chips now didn't meet spec for the chips that they were supposed to be. And the thing with that is like, so what if my chip here is, so, based on that, you would assume some chips actually degrade slower than other chips. And then, so some chips are more susceptible to degradation than others, because obviously degradation is based on the physical properties of the chip, of the wiring, of the transistors. And those are also subject to the silicon lottery. So, like how max clock speed is subject to the silicon lottery, degradation rate is also subject to the silicon lottery. So this thing, taking 67 hours to degrade at these absolutely insane settings of over 107 degrees operating temperature with current draw in the, and that's actual proper current draw right there. Like if we ask to look at the VRM sensor, this thing is pulling, peaks at 115 amps and currently hovering around 111 amps. I mean, if we set the average, like actually I noted down what kind of currents I was averaging. And the thing is, the current draw goes up as the operating temperature goes up. So at warmer temperatures, this thing would be averaging 114 amps. And the lowest current draw test that I was running was 107 amps, and that was the first test I ran that ran for like 5 hours. After those 5 hours, I decided this wasn't going fast enough, so I cranked it up to 110, because, you know, I was aiming for 100 megahertz worth of degradation in 24 hours, so after 5 hours, I should have lost 25 megahertz. Now, you might be like, is degradation linear? It really shouldn't be. Like, electromigration should actually cause more electromigration, assuming you're causing electromigration stress. And actually, like, I think all of the degradation effects ramp themselves up. But electromigration definitely does, because as you get electromigration, it wears down the metal layers of the CPU. So there's now less metal in the metal layer. Like, the metal layers are now more unevenly distributed. And so there are, like, the areas that were already experiencing, you know, electromigration where material was moving away. Well, now those areas are thinner, they have more resistance, and they're even more susceptible to electromigration. So electromigration should actually lead to more electromigration. So there's a pretty decent chance that, you know, it might have taken me 67 hours to shave off 25, 50 megahertz. It might only take 40 hours to shave off the next 25 megahertz, but I don't know. I don't know where I am on the curve. 1 point, you know, a curve does not 1 point of data a curve does not make. And also, any curve is looks linear if you're, you know, looking at it at the wrong scale. So that's kind of really annoying with this. Is just like, yeah, I don't know where I am on the, like, degradation rate curve. At 67 hours, 25 megahertz. I don't know how long it's going to take to lose the next 25 megahertz. What else is there? So there's also the whole issue of, like, is my chip good? Is my chip bad? Is, you know, as I mentioned, like 200, like a real world endurance test, you know, they ran 200 chips and you had like six of them fail after 1,000 hours. And also the failures weren't like all at the end of the 1,000 hours. They had like, there was like one chip that failed in the first 10 hours. And by failed, I don't mean died. I mean degraded to the point of no longer meeting specification. So you had one chip in the first 10 hours that fell outside of spec. Then you had like two or three chips in the next, you know, 100 hours that fell outside of spec. And then at the end of the 1,000 hours, you had another two or three chips that fell outside of spec again. And the thing is just like, okay, so that's like, you know, and the thing is like, that's falling out of spec. That's not like, they weren't testing, are the chips like, what rate are the chips degrading at? They were like, they weren't measuring like megahertz lost per X hour, like per unit of time. They were testing number of chips lost to below specification. So if you had a bunch of chips that were, because there's a safety margin built into every CPU specification. That's why, like, you can undervolt any silicon. Why you can overclock any silicon is because there's a massive safety margin, normally in the range of 50 to 100 millivolts, so that if something goes horribly wrong, you've got 100 millivolts of reserve where it's like, yeah, it's actually just fine. But anyway, so basically degradation is kind of inconsistent, and, you know, doing it on one CPU or is kind of pointless, because it doesn't really tell us anything about how other CPUs might respond and how long, you know, how quickly this is going. Other issues with this testing, I don't know how much of an effect the temperature has. I don't know how much of an effect the current has. I don't know how much of an effect the voltage has. Now, because the thing is, voltage and current actually cause sort of separate degradation effects, though current is a result of operating voltage and load. So you can run, you know, so like voltage on its own will cause degradation. If you just set it high enough, you're just going to start blowing holes through the insulator layers in the silicon. But based on how the boost algorithm behaves on Ryzen CPUs, I would assume that Ryzen CPU, like the insulator layers in Ryzen chips, are actually really, really sturdy. And so I'm not too concerned about the voltage, which is why I'm, you know, running this through Prime 95 at insane temperatures, because I suspect, like, based on how the boost algorithm behaves, I suspect Ryzen is primarily susceptible to electromigration. Because if I run this chip in Prime 95 with these Prime 95 settings on like the boost algorithm, on the precision boost overdrive system, it'll top out at 94 amps. It won't go over 94 amps, no matter, like, the max current draw is 94. It'll hover closer to 90, and my 3950X is the same way. It doesn't really like to run Prime 95 above 180 amps. Then, you know, my 3600, I can't remember. I didn't bother to note down the current draw, but so my suspicion is Ryzen is electromigration sensitive. It's not particularly voltage sensitive. Now, unfortunately, voltage sensitivity goes up as operating temperatures go up, and electromigration rate goes up with operating temperature as well. So the fact that I'm running this at 107 degrees makes this testing completely useless for predicting lifespan at 95 degrees because the effects of the temperature are going to be non-linear, is my assumption, because unfortunately most effects are non-linear in this world. So if that's non-linear, I have no idea what would happen at 95 degrees. And even if it was linear, I wouldn't know what the slope is, right? Like, I don't know what the slope is from 100 to 95 degrees, so that's not great. So yeah, and then the current draw. We are 20. I think it's close to like 20% over what the chip would normally pull. Or well, okay, let's just go 111 divided by 94. Yeah, we're close to like 20% over where PBO tops out. And as far as I know, the rate of electromigration due to current is also not it's not exactly linear either. So, you know, in terms of actually like long-term, like in terms of extrapolating useful long-term use data from this test, useless, completely bloody useless. I'd need to run like 100 chips at different temperatures for like 1,000 hours. Like you'd need to, because I'm not controlling for variables here properly, right? Like we're running, like the voltage affects the current and the voltage affect the temperature. And so it's like my temperature's out of control. This is like we're at 108. There's nothing I can really do about it. Ideally, what you'd want to do is you'd want to run a test where you hold all of the CPUs at exactly the same temperature and then just vary the voltage and current. And, well, good luck with that. Actually, that wouldn't be so hard. Like, if your goal was to run all the CPUs at 110 degrees, you could just steadily make the cooling system worse, right? Like, the CPUs with less voltage would have a worse cooling system to get them to the same temperature as the CPUs with the better cooling system. And then you'd maybe finally get some data that gives you some representation of like voltage and current degradation that you could actually like scale into something usable, but you'd still have to do it on an absolutely insane number of CPUs because, as I mentioned before, you know, on like an actual real world reliability test, like a real manufacturer's reliability test, you had like 3% of chips that died out of 200, which is like, you need a lot of chips to have something that's like valid for a large number of CPUs and not just the CPUs you're testing yourself. So at this point, you might be asking yourselves, is there any value to this data whatsoever? Well, for me, what this means, like this test, for me, what this means is I don't have to be anywhere near as careful with my 3950X and 5950X as I thought I have to be. And the reasoning for that is very simple. This is like so far from optimal settings, and it's taking so freaking long to degrade that, you know, running like 3D Mark or something at the, like if I was running 3D Mark at 1.45 volts, and by that I don't mean TimeSpy, but TimeSpy's physics test is a little bit heavier. So like if I was running like Firestrike physics at 1.45 volts, it would be fine. Like I'd have probably, like this is taking 67 hours. Like we'd probably be only pulling like 90 amps. Maybe less than that per CCD. Like we would potentially be within like the stock power limit of the CPU. Right? Like that's the thing is like right now, like my goal was to violate the stock specification of the chip as much as possible. And now admittedly this is a 3700X, so it's technically has like a 65 watt power. I mean, it has a nominally it's a 65 watt chip with an 88 watt power limit. But the thing is, AMD also makes the 3800X, which is a 105 watt chip with a 140 watt power limit. So my goal was to get this as far past the 140 watt power limit as possible. We're way above that, right? Like CPU package power draw is reporting 180 watts, and you know, of that 180 watts, like 160 of that goes straight into the CPU cores. So yeah, this thing is getting burnt to the ground. But yeah, this is taking forever. So based on this, you know, if you're just benchmarking, like you should be able to run some pretty like, especially if you're not going over 100 degrees, because the operating temperature should actually play a major role in the electromigration effects, because well, we're not going to get into that. I have a whole video going over like degradation effects, but yeah, so the operating temperature should play a major role in the electromigration. So it's like if you're running reasonable temperatures and you're just running benchmarks which don't pull very much current, which most of them don't, like even Cinebench doesn't pull anything. Like if we stop this, all right, so we're going to stop. So this is currently pulling like 111 amps. So we're just going to stop Prime 95. And we're going to run Cinebench now, because Cinebench is a joke. So that was pulling 111 amps, right? Yeah, our average current was still over 110 there. Oh no. Well, whatever. Too late. So now the average is coming down because we're idling. But anyway, let's run Cinebench. And we're going to scroll down to the VRM sensor because I don't really like the 70 amps. It's nothing. It's not pulling any bloody current. Like, it's literally, like, it's not pulling any freaking current. It's also running at, what, 80 degrees. You could probably run this indefinitely based on my test. Right? Like, you could probably run this at 80 degrees, like, 70-ish amps. Like, assuming, because here's the thing, I'm assuming that Ryzen is susceptible to electromigration. This should probably be runnable almost indefinitely. And like, yeah, we're at 1.46 volts, but if you've ever observed a Ryzen running a single-threaded workload, or even just a very light workload, it doesn't need to be necessarily single-threaded, the chip will happily go to like 1.47 volts on its own, on the boost system. So yeah, I'm really not very concerned by this. Because that's kind of the thing, but yeah, because like the freaking Cinebench doesn't pull any current. It was like, yeah, it's like 70 amps. So, but unfortunately, I don't know. Like I don't know what the curve is. But the fit limit doesn't like going over 90. And it also doesn't like going over 95 degrees. In fact, like as you approach 95 degrees, it already starts drastically reducing the current draw, which I'm not sure if that's because it wants to stop at 95 degrees Celsius or because it's like derating based on the operating temperature. So yeah, unfortunately, one data point does not a graph make. And by that, I don't mean a bar graph. I mean like a line graph, because we're measuring lifespans here. That's a good type of graph. Line graphs are good. Bar graphs, terrible. But yeah, like, so based on this, for long-term use, I still don't really, like, the issue is, like, you still want to stress test with something heavy, right? And especially if you're going to be running the CPU in heavy multi-core workloads, I think your goal should be like, your workload should not be going above the current draw that PBO normally hits. And your current draw goes up really quickly with operating temperature. So if you're running the chip hot, your current draw goes up. Especially, like, the thing is, the effect of the operating temperature on your current draw is non-linear. So going from like 10 degrees to 20 degrees Celsius, not a big deal. Going from 20 to 30, slightly bigger deal than 10 to 20. Going from 30 to 40, even bigger than, 20 to 30. And it just keeps getting worse and worse. And then towards the top of that curve, it just gets kind of ridiculous. Though I've not, like, I have liquid nitrogen. I could technically make a graph of that quite easily. Yeah, that's not exactly something super difficult to make a graph of if you have liquid nitrogen. Like, I could just run Prime 95 and then just pull the temperature down slowly and record the reported current draw for, on an average of like 2 minutes or something. Man, that's going to suck up so much nitrogen, though. No, not really. It's like 180 watt CPU. That's not really that big a deal. So, where was I going with this? Yeah, so Ryzen is actually surprisingly difficult to degrade, but at the same time, this is 67 hours. And also, I'm not testing, like, the thing is, I didn't minimize the voltage for that 4.17 gigahertz pass. I just went with, like, what frequency can we hit at 1.35 volts with medium LLC, and then I just kept lowering the frequency until it was passing Cinebench consistently. So there's a chance that, you know, the degradation's a bit worse than that, because I didn't necessarily minimize the voltage for 4.175, but yeah, like, based on this, I would still generally, like I'm kind of looking at this like, okay, so let's say you had a 3700X, and, like, you still want to run a good amount of V-droop, in my opinion. The chip is also, like, not very coolable once you go over, like, if you're hitting 1.35 load in Prime 95, it's going to run really, really freaking hot. I mean, we can test that. And we can extrapolate most of, like, I would assume we can extrapolate a lot of this behavior to the 5000 series, or, like, assume that the 5000 series isn't really that different because it's on 7 nanometer. There's not much to extrapolate. We don't have a curve. The other thing is the chips don't scale. Like, at the top end of the voltage, like, at 1.5 volts, this chip doesn't scale, like, clock any better than it does, or, well, for Prime 95, it doesn't clock any better than it does on, like, 1.35 volts. So, yeah, that's the other thing, is, like, if your operating temperature is really high, it actually kills your clock speed. So, yeah, there's not a ton of point in that. So that was 1.5 volts, so, and that was dropping to 1.44, so if we set, like, 1.4 volts, like, if I was on like, for daily use with the 3950X, the big issue is, like, cooling it. Like, I don't think it's really voltage limited there, it's just cooling. Like, those chips, like, the thing is, the 7 nanometer CCDs do not do a good job of dissipating heat at all. So, yeah, if you just whack one of those really hard, like my 3950X hits 90 degrees at 1.2 volts. Easy. So, you know, it's not like I can really go above 1.25 volts, because it'll just end up going over 100. Also, the reason I use 128K FFT size specifically is because it runs really freaking hot. The smaller FFT sizes run a little bit cooler, and the larger FFT sizes also tend to run a little bit cooler. So yeah, this is doing 94 amps, and we're running... So that's still within the PBO limit. Oh, that's because we're at 4.1. Well, no, that's slightly above PBO for this chip. Let's check the notes. Yeah, so PBO would be hitting 1.29 volts, 94 amps at 84 degrees Celsius. We're hitting 95 amps at 90 degrees Celsius with 1.35 volts. Also, we're running a 50 megahertz higher core clock compared to PBO, which, well, I mean, let's see. Let's see if we can run 4.2, because PBO on this chip on auto would hit 4.05 gigahertz. So it's like, if you're not going above the stock frequency by a significant amount, you are wasting your time as far as I'm concerned. But yeah, for benchmarking purposes, I think this data is great, because it's like, unless you're absolutely just demolishing your chip, it should take many, many hours before you start seeing noticeable degradation. Nope, that's the wrong button. I don't think it's going to run 4.2. It barely runs 4.2 in Cinebench. Actually, it doesn't run 4.2 in Cinebench. Oh, now that I've degraded it, I've made it worse. Ooh, I wonder if it slowed down on PBO. I don't think it did, though. Because 4.05 at 1.3 volts, like, that's a lot of headroom. Right? Like, this chip does 4.1 at 1.3, easy. It does, like, for Cinebench, it does 4.175. So, well, it doesn't anymore, but it did before. So PBO really, like PBO, like I said, there's a massive safety margin built into your stock, like your CPU at stock. That's just how that works. So yeah, considering the safety margin, I don't think this will like even be affected on stock settings right now because of the safety margin. Funnily enough, this chip already didn't run at stock on some other boards, which is kind of whack. Okay, so immediately we're losing workers and the whole thing went down. So the blue screens have gotten a lot more interesting since I've like run this chip at like hellfire voltages for 67 hours. Like it used to be like I've never seen that blue screen before, for example. I have no idea what that is. I mean, actually no, I have a rough idea. It's too much core clock, but like I've never seen that. Also, Cinebench actually crashed out with an IRQL not less or equal for me, which is normally a memory error, but like I got it for the core. So I wonder if the cache is like melting. Right? Because like IRQL not less or equal is normally a memory error. The L3 cache, as far as I know, runs off of vCore. So if I've been burning down everything powered by vCore, the cache is probably gone. Which might explain why the blue screens look more like memory errors than what, you know, like, because normally if the CPU hard crashes, it just black screens and there's no blue screen, for Ryzen at least. You know what? Let's see PBO. I want to see PBO in action, so we're just going to put this back to auto. I think PBO is actually still enabled. I don't think yeah, it's still on, so. Also, I wouldn't use the 10x scaler. In my experience, the 10x scaler does, like, it raises the low core count voltages, but for high core count, it doesn't give you any benefits. I wonder if that would be interesting if it was actually like primarily the L3 cache that was failing, or some other cache. It doesn't necessarily like I assume it's the L3 because that's like the biggest part of the chip. Like most of the, as if I remember, yeah, I think most of the CCD is L3 cache, like other than the actual core logic itself. Oh come on. Well, actually, we don't really need hardware info. We can just try run Prime 95 and see it crash instantly. Oh, wow, it's still running. I wonder what kind of temperature it's hitting. What kind of current draw? Yeah, now it's pulling 100 amps. So we're outside of the PBO, actually 106. And as the temperature crawls up, the power draw is going to go up as well. Now, admittedly, Prime 95 is extremely heavy, but there are workloads that get pretty close to Prime 95 levels of load. And so, well, I get, like, I guess it really depends on the use case. Wait, now it's only reading a 90 amps. Did we lose a thread? Wait, was I looking at the wrong current? Oh, no, that's... Oh, man. I don't know why we have a CPU EDC reading. Like, I don't have any idea what that is, because it's off by, like, 20 amps almost always. Or, like, what is it, 16 amps right now? Yeah. Like, it's always off by some random amount of current, and I have no idea why it does that. Oh, so we're pulling 90 amps right now, so that's actually not too bad. I wonder if we've, like, No, it's loaded up properly. Wait, we're at 4.0. Oh, because, right, I put it on PBO, not manual overclock. I'm stupid. I'm so stupid. I completely forgot what we were testing here. Yeah, so this is what PBO likes to do. And it's actually at lower temperatures right now, and it's still not boosting the current draw. Yeah, so PBO really doesn't like going over 90 amps for some reason, and my guess would be the electromigration. It's pretty happy to run, high voltages. I mean, that's high voltages is 1.3 volts, which, is 140 millivolts less than what I was running. But say I stop this. Like, it immediately just shoots up to 1.48. Like, so that's the thing is, like, I really don't think Ryzen is that sensitive to voltage in and of itself. I think it's primarily, we're just going to run 2 threads. And yeah, it sits at 1.4. Admittedly, at 75 degrees. That's 25 amps. According to that reading, current out 27 down here. 26. On 1.4 volts. 27. Is the temperature going up? No, it's still at 74 degrees. 28. Why does the current keep climbing? It shouldn't really be doing that. I guess it's based on like how it's. Oh, I guess it might be hopping the thread around and like boosting the different cores up and down. So that might be screwing with the current reading. But okay, so we have like 2 cores loaded right now, and it's pulling like 50, almost 15 amps a core. Or if we're gonna be nice to it, we're gonna say 13 amps a core. Wait, now it hit 37. What? Why is the current going out of control right now? I get the feeling the software bugs out sometimes. Or maybe Windows is just doing stuff in the background that we can't see. Yeah, because we really should be at like 12.5% CPU load, and we're at 15, so that's not really super accurate. 30 amps. The voltage keeps going up. We are still running 2 threads, right? Like... Oh man, it keeps like the also I think the shuffling of threads around on Ryzen CPUs might be some kind of like like degradation leveling thing to make sure that like no core gets burnt down on its own. Yeah, so now the temperature's down and the current draw, but let's say so that's like 13 amps. Right? And if you scale that up to the whole chip, that's significantly more than the 90 amps that it normally tops out at. Actually, now it's back up at 30. Man. Boost system just doesn't make up its mind how much current it wants to pull. So, let's say, I don't know, like what should I say about that? So it pulls like 13 to 15 amps. So 13 times 8 would be 104 amps for the entire CCD, which it never hits on its own. And 15 times 8 is 120 amps, which is like completely bloody uncoolable. There is no way you're pulling 120 amps, because as I showed, like at 111, the thing was like at 108 degrees. So you're not doing that. That's just no. So yeah, I'm not like, so that's kind of the thing is like, so watching, how the voltage is quite happy to be really high, and the per core current, like, we're running 2 cores right now. Each of those cores has to be pulling like 15 amps almost. And it's really like, it's perfectly happy to do that. So my assumption with Ryzen is that it's not really very concerned about like I would assume it's like some main power distribution thing that fails when you hammer it. Like the individual cores aren't particularly sensitive to electromigration, but the whole, like the CCD as a whole is. And then the whole thing isn't really sensitive to voltage because, well, actually right now the DLDOs might actually be doing so. Well, no, because none of the cores are idling. So, fun fact, Ryzen has built in like digital LDOs. for some power management, but as far as I know, for desktop chips, they're never used for voltage regulation. They're just running as on-off gate. Like they turn, like they're basically just on-off switches. So cores either get power or they don't get power, and there's no in between for that. So yeah, that's kind of fun. So anyway, yeah, you can definitely degrade a Ryzen, but if you think you degraded your Ryzen's chip in like, because the thing is, there's like a bunch of forum posts out there where people are like, oh, I degraded my chip at 1.35 volts in like a week, and it's just like, what? Like, either my chip is like incredibly resistant to degradation, or you're just bad at measuring, because it took me 67 freaking hours at like over 100 degrees with 111 amps to degrade my chip by 25 megahertz. So yeah, like the short term like crazy high degradation thing, I don't think that's a thing. There's maybe a chance that like AMD's QA doesn't catch all the dodge, like maybe you know that they have a higher. Well, no, because the various retailers say that the RMA rates are normal. So yeah, I don't know. Like I don't think like if you think you degraded your chip in a week, you probably didn't, unless you did something incredibly stupid, or you have a motherboard that like doesn't listen to what you're like doesn't follow the settings properly, and like and it's not like there's some motherboards that'll automatically set your voltages for you, and they'll often set them way too high. So I'm thinking of something like that because that's actually like one of the ways I accidentally. My first dead CPU was when a motherboard decided to blow up my North Bridge without telling me about it. So that was and that yeah, so that was fun. So yeah, anyway, like, not a particularly useful experiment, in my opinion. But the thing is, it's not really a loss because the only thing on the CPU that I care about is the memory controller. And thanks to, like, the memory controller is literally not part of the core. Right? Like, it's a completely separate piece of silicon. So I'm not too concerned about doing this because the memory controller is perfectly fine. And that's literally the only reason, like, the only good part of this entire CPU is the memory controller. And I guess the Infinity Fabric, but I would assume the Infinity Fabric's still okay. We're not going to test that right now. But, yeah, so degrading Ryzen, is it possible? Yes. Is it, like, if you want to do it quickly, you need to be absolutely, like, insane. Honestly, I don't think, like, if you tried to do what I did here with the 8-core, if you tried to do this on a 16-core, it'll just thermal shut down. Like, I don't think you'd be able to do what I did just because it'll shut down on you before you get there. Because, yeah, like, this thing was running 107 degrees at, like, 180 watts package power. If you ran this on a 16-core, you'd be pulling somewhere around 360 watts. Like, the thing would just shut down. There's no way you're cooling it. At all. So with the 16 core, like actually I know for a fact that if you want to like hit like over 100 degrees on the 16 core, you only need like 1.35 volts to do it. In Prime 95, and at 1.35 volts, your current draw is going to be significantly lower. So even though the temperature is going to be really high, like it should still take a while before you get to the same level of degradation that I did. Now, I don't know how much longer. I don't know if it's going to take 2 times longer or 10 times longer. Maybe 20 times longer. I have no idea. One point of data does not a curve make. But, yeah, like, and for long-term use, I still think it's just kind of, like, the chips don't scale that much with voltage on the high end. So, like, so, like that. The thing is like I'm thinking about this like, well, if you're a gamer, right, and you only play games, and your games aren't super multi-threaded, then yeah, you could probably get away with some settings that would be completely unsafe for somebody who's like a 3D artist or something, or does regular, you know, heavy video encoding on all cores. But if you're Like if you're actually using your 16 core, you can't run that much voltage into it because it'll run insanely bloody hot, and that alone is already not great for the chip's lifespan. So yeah, like the 16 core at high load, like you're gonna be at what, like 1.25 is like barely coolable. I mean, even actually no, 1.2 in Prime 95 is insanely hard to cool. 1.25 is like, yeah, for lighter workloads you can probably get away with it. I guess you could run your, like, you could do the Intel thing of like, I know that I'm never going to run a workload that's like, all my workloads are like 90% of the load of Prime 95. So if Prime 95 is slightly overheating, that's fine. And then, so you can do your validation in Prime 95 in like three or like a couple, well, I don't know. The thing is, if you're running like really important, like if you're doing work, where it's like a render for 24 hours or something, you really don't want that crashing. So at that point, it's like, wouldn't you really want to validate that for like 24 hours with some kind of stress test that's heavier than whatever rendering workload you're going to run? Because like you're going to lose 24 hours of render time potentially if it isn't perfectly stable. So at that point, you have to ask yourself, are you even going to are you even going to overclock? So, like, ultimately, I don't think I'm changing my voltage recommendations. I like, for long-term use, I still say follow the frickin' fit limit. Like, this chip fit limit is 1.29 volts, 94 amps. Therefore, if I'm going to overclock this thing with medium LLC, I'm going to set it to 1.35 volts. It's going to V-droop to 1.2-ish, 1.29, 1.3-ish in Prime 95, thanks to the V-droop. Which is good for the load, which is good for the transient response, and we don't have to worry about the, and temperature wise, it's going to be fine. And then I'm just going to overclock it on that level of voltage and call it a day. And I don't really see a reason for it to degrade, even though I might end up running slightly more current than what the boost limit, than what the boost algorithm would naturally go up to. And then if you're running if you're running a 16 core, you're just going to hit the cooling limit first, I think. And again, you can just use the fit. Like, the cool thing about the precision boost algorithm and the boost override system is that if your cooling system sucks, it'll tell you, because your your max voltage when doing a fit test will be way lower based on how bad your cooling system is. Like, if you run a bad enough cooling system, the fit limit will be like 1.1 volts. Because like the chip will keep lowering the voltage as long as the temperature is too high. So yeah, but for short-term benchmarking, based on this stress, like this 67-hour torture test, yeah, I don't think I'm too worried about mashing 1.45 volts through 3D Mark, or even 1.5, though I don't think it'll scale. Like, I don't think 1.5 volts is going to make the chip clock any higher. But, that'll depend on a chip-to-chip basis, and also workload to workload, because something like the lighter the workload and the lower the operating temperature, the higher the voltage you're going to be capable of scaling to. So, yeah, and this video is now way longer than I was planning it to be, but hopefully this is somewhat useful. Even though I'm still, like, it's one data point. Like in the grand scheme of things, maybe this chip is like super resistant to degradation, and everything I've just said is completely unsafe, and this thing is an anomaly for not being down 500 megahertz or something. But hey, no, like the fit limit. Just follow the bloody fit limit. Run PBO, see where it tops out in terms of voltage and current, and then just kind of stay near that. Like, if you're feeling brave, you can go maybe 5% above the boost current limit. If you're not feeling brave, stay at the current limit. You can still get a bunch more frequency for multi-core workloads because, again, even when you're using boost override, the thing still has that built-in, safety margin for, like, degradation. So the chip won't come out, that's why, like, I can run Prime 95 at 4.1 gigahertz, but the boost algorithm tops out at 4.05. Right? Like, there's a 50 megahertz, maybe more than that, frequency margin that AMD left on the table as a safety margin for crappy motherboards and chips that degrade at an accelerated rate to what they expected, or suboptimal operating conditions. And and whatever else. So yeah. Anyway, that's it for the video. So my already terrible 3700X is now ever so slightly worse. And hopefully this was somewhat useful. So yeah, thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below if you'd like to support what I do here with actually hardcore overclocking, which will not, like, it will not go into abusing any more CPUs like this. I think that, like, this is so bloody pointless. Like, we have no useful data. Like, again, well, okay, it's not no useful data, but mostly useless data, right? Mostly useless data. For long-term use, this doesn't tell us bloody anything. And for short-term use, I guess it's for short-term use, this is a nice reassurance that you can kind of do silly things for benchmarks, but yeah, it's still not great. But so if you'd like to support me, I have a Patreon. It will not go towards funding more CPU abuse like this because this is bloody pointless unless you do it with like 200 of them. And if I could afford to buy 200 of them, then, if by some miracle we get to the point where I can run a 200 CPU torture test, we might do that. But otherwise, no, because it's pointless. There's too much variance, not enough data, not like... And even with 200 chips, you'd probably want to run some chips at, like, as I mentioned at the start, like, you'd want to run them at, like, the same temperature but different voltage settings so that you can control for, like, your temperature. Like, the temperature is the easy one to control because you can scale up the cooling system. The current, on the other hand, is directly tied to how much voltage you're running, so you don't really have a choice. If you want to run 111 amps, there's not really that many ways to hit 111 amps other than 1.44 volts in the case of this 3700X. So that's kind of that. Where was I going with this? But yeah, so, at that point, like, if you had enough CPUs, you could actually start running them at different settings and then monitor how quickly some chips are degrading compared to other chips. And then you'd get a nice degradation curve, and you'd actually have something useful for long-term extrapolations, and you could judge how, conservative the boost system is based on that. But as it is, Ryzen pretty tough, maybe, I guess, maybe, like 67 hours at insane settings. But anyway, right, this was supposed to be a Patreon plug. Patreon, in the description, goes towards not doing this, but all the other stuff on the channel, it goes towards that, like acquiring hardware and RAM and the kind of thing. So, and then there's also the AHOC Teespring store where you can pick up shirts, stickers, posters, the usual YouTuber merch. Both the Patreon and the Teespring help out immensely with running the channel. Because otherwise, how else would I afford to do things like this with a 3700X? Well, actually, like, this chip sucks. It's still not a loss. The memory controller still works. That's all it ever needs to do. Anyway, yeah, Teespring, Patreon, links in the description. Thanks for watching, and goodbye. That's the wrong mouse. There's the stop button.